Okay, so last time we started talking about the sample quantile, and we give you an important lemma, which we stated the conclusion but didn't prove it. So this lemma is to connect some ratios of partial sums for IID exponential 1 random variables. So we have y1 to yn plus 1 IID exponential 1. And we define SI as y1 taking sum up to yi, this partial sum. And the conclusion is that if we have u1 to un IID from uniform 0 to 1, and we order them as order statistics from the smallest to the largest, then the conclusion is that if we look at the ratios of S1 over Sm plus 1, so basically S1 is just y1 alone, Sm plus 1 is the total sum to Sn over Sm plus 1, conditional on Sm plus 1. So the conditional distribution of this n-dimensional vector has the same distribution as u1 to un, the n-order statistics. Okay, so to prove this statement, and why is it important? You know, our goal for sample quantile is to develop the asymptotics of sample quantiles. And we know that, let me say the rationale of caring about this result is that if we are interested in the sample quantile, let's say we have IID, okay, and what is the sample quantile for the pth quantile? Sample pth quantile for p between 0 and 1, not taking 0, 1, no, because they are at the extremes. They are the extreme order statistics. But if it's just somewhere in the middle, then what does it correspond to? Last time we said it's defined as the order statistic of the order as the ceiling of n times p, the smallest integer that's larger or equal than n times p. That's how we define the sample quantile. And we know that if we think about the map from uniform random variable to this X distribution. Okay, let's say that if they are IID from some distribution f with CDF function f, then what do we have? We actually know this X and P order has the same distribution as the F inverse transpose of this uniform samples order statistics NP. This is the key. So because of this important result, we know that we can convert a uniform random variable to the variable of our choice based on the inverse of the CDF. That's what we saw before, right? Then we can easily connect the distribution of this uniform sample quantile to the sample quantile by interest. So that's why we care about the uniform order statistics, which is here. That's the rationale. And given this, our target is to derive the uniform order statistics distribution, but we want to connect them to here. Why is that? The reason is it's not easy to work with order statistics, but it's much easier to work with partial sums. Since you know the sum is a sum of IIDs, and we know that central limit theorem gives us the powerful tool for handling the sum. So that will give us the basis for asymptotics. That as long as we know the asymptotic distribution for partial sums, then we can map partial sums to those ratios by just a map, right? And we know that to handle the map, we can use delta method that can give us the asymptotics for those ratios. And finally, we will have asymptotics for the uniform order statistics. So that's the whole logic. But to prove this lemma, we will use basic techniques. That is, we're going to show that the conditional density of the left-hand side is equal to the density of the right-hand side. So first, let me ask you a question. What is the density of this order statistics vector? So probability density function of this, okay? I use the lowercase f for the vector u1 to un. If I evaluate them at lowercase u1 to lowercase un, at those n values, what would be the density? Any idea? So this is telling me what is the probability density for the smallest order to take value u1, the largest order to take value un, right? I do need an agreement. Oh, sorry, I do need to have some condition to make this density non-zero. First of all, to have a non-zero density, then because order statistics, u1 to un follow a monotone increasing order, so these values must follow that order. Otherwise, they couldn't be the values that my order statistic vector that can take. So the first one is the indicator that I need to have I need those values to satisfy this condition. And there must be no tie. The reason is that the probability uniform is a continuous distribution. So for two order statistics to pick one value, the chance is 0 actually. But actually, it's a little bit more complicated than I just said. But we can just say this, right? The indicator is that these n values are, there's no tie, and they're between 0 and 1 for simplicity. But now I think double thought about it, I think maybe we could allow ties, but I think that's a minor issue here. So, but following this monotone trend is the key to make sure they are valid values for order statistics. Okay, and then what else do I have? You see, basically, I need to match those n random variables to those n values, right? Now, how many chances can I have those values? What's the difference between the density of the order statistics and the density of just u1 to un, the IID random variables evaluated at these n values? Or maybe I should make this more clearly uppercase. What's the density of this? And let me ask you this question first. And still under this condition, if that's the case. So when I have all the u1 to un ordered and between 0 and 1, then they are IIDs, okay? Then the density is just the product of their individual densities, right? And that's 1, because they're all uniform 0 to 1. So each random variable's density is 1. So I have 1, that's the density. What's the difference between here and here? The thing is that if I shuffle those n values, my order statistics will still take the same u1 to un values because they will be ordered. So the key here is that these things are not ordered. So they may pick any shuffle of u1 to un, but still they will give me the same order statistics. And how many times of shuffling can I have for those n unique values? N factorial. So that's why is n factorial. So that's the density for this order statistic. Okay, but obviously, even though we derive this probability density function, we cannot use it for asymptotics. The reason is that this density function depends on n, and n is divergent. So to us, this is not something meaningful. But we will use this to prove this lemma. So for this lemma, what's left for us to prove is that the left-hand side, the conditional density also takes this form. Then we're done. Okay, so how do we start? Let's first start with exponential 1 IID. Okay, so let's first start with the density function of y1 to yn plus 1. This vector evaluated at y1 to yn plus 1. This based on IID, and the density function of exponential 1 would just be exponential to the negative summation I from 1 to n plus 1. That's what I have. And also, because of the support of exponential distribution, I need to multiply by an indicator that y1 is positive and yn plus 1 is positive. They're all positive. Okay, I start from here, and then I need to go to the partial sum. Okay, then how about the partial sum? Let's say I look at the density. I first look at this partial sum S1 to Sm plus 1. This, and I evaluate this n-dimensional, n plus 1 dimensional vector at values lowercase x1 to Sm plus 1. And how do I link them? I need the change of variable to get the density for this from here. Okay, and what's the change of variable here? So clearly you see S1 to Sm plus 1. Or maybe it's easier to go the other way. The other way is how can I go from here to here? So you see y1 to yn plus 1. What is y1? Y1 can be written as S2 minus S1, okay? And y2 is S3 minus S2. And finally, yn plus 1 is Sn plus 1 minus Sn. Okay, so in this case, given the relationship between this and this, I can actually say, okay, y1, y2 to yn plus 1 is a function, I say function h of S1, S2 to Sm plus 1. Okay, given this relationship, then what can I say? Yeah.
The first vector was 1.
Oh, sorry. I think I missed. Yeah, so it should be S1 and S2 minus S1 and so on. Yeah. So given this relationship, how can we find the density of S1 to Sn plus 1 based on the density of y1 to y2 to yn plus 1? So we know that there is a relationship we said last time, which is we can have this equal to the density of y1 to yn plus 1 evaluated at this h function of S1 to Sn plus 1. So be careful that inside the density, we always have lowercase symbols. Outside, we have the subscript as the uppercase to indicate the random variable. So lowercase for the values and uppercase for the random variables. So we have this, and also we need to multiply by what we call the Jacobian, which is what we have, the H dot at S1 to Sn plus 1. The Jacobian is the absolute determinant of this matrix, H dot matrix. So what is H dot matrix here? Let's see. Right, so it'll be an n plus 1 by n plus 1 matrix. So clearly you see for the first row, it's the S1 taking the partial derivative for S1, S2, and Sn plus 1. So since it's only S1, we have 1 and 0 afterwards. Okay, for the second element, that's for the second row, we have a negative 1 for S1, 1 for S2, and 0 afterwards. And finally, you see in the last row, we are going to have a negative 1 for Sn and 1 for Sn plus 1. So this matrix is a lower triangular matrix, right? So we only have non-zero entries on or below the diagonal. So, and on the diagonal, we have all ones. So therefore, its determinant is just 1. So that's why this is equal to 1. So therefore, you see, we can just apply the density function here, but replace the arguments by this H function, which is S1, S2 minus S1, and Sn plus 1 minus Sn. So therefore, it's just, let me write here, y fy1 to yn plus 1 evaluated at S1, S2 minus S1 to Sn plus 1 minus Sn, okay? And then putting this as y1 to yn plus 1 here, what do we get? If we take the sum of those n values, we just have Sn plus 1 because the next one will cancel the previous one and so on. So therefore, the density is exponential negative Sn plus 1. Okay, and the condition, the indicator function, you know, this translates to here. It means everything must be positive. So I would have indicator that 0 is less than S1, less than S2, less than Sn plus 1. So they are equivalent to each other. Okay, so now we have the density function for the partial sums, S1 to Sn plus 1. Do we have a question? So just separate this a little bit. Now let's move on to the ratios. So to obtain this conditional density, our goal is to first obtain the joint density of the n ratios and this Sn plus 1. So we still have n plus 1 dimensional vectors. So let me say that I denote this Zi, okay, equals to Si over Sn plus 1 for I from 1 to n. With this notation, then the next density I'm interested in getting is F at Z1 to Zn and Sn plus 1. Okay, and I want to evaluate them at Z1 to Zn Sn plus 1. So it's very tedious, right? To evaluate this at this density. And again, we are going to go with the relationship, you know, between, I'm going to erase this part. Okay, Z1 to Zn Sn plus 1. Its relationship to the S1, S2 to Sn plus 1. So what is the relationship? Obviously, this is S1 over Sn plus 1. This is Sn over Sn plus 1. Finally, Sn plus 1. Okay, now I'm going to call this a g function of S1 to Sn and Sn plus 1. With this g function, I can go from the density of this S1 to Sn plus 1 to the density I need, Z1 to Zn and Sn plus 1. Okay, so what's the g function? It's in this form, right? We specify it. That's the definition of g function. How about the Jacobian? Let's take the derivatives again. So S1 to Sn plus 1, or Sn and Sn plus 1. So this is again an n plus 1 by n plus 1 matrix. The first row, taking derivative against Sn S1. What is that? We actually have it as what? Can we see it? Sorry, I think I made a mistake. My bad. I think I made a mistake. Sorry, I should go from right. What I need is that I need to, this is the thing I need. I need to go from Z to S. Sorry. So that's how I need for the change of variables. I reverse the order. So I need to see, okay, S1 to Sm. How can I go from Z1 to Zn to this? Okay, so this is also obvious by definition. To obtain S1 from this vector, I need Z1 times Sn plus 1 to start with. Lastly, I need Zn times Sn plus 1 to start with. Okay, so this way I can go from Z, my target, to S, what I have. So therefore, when I take the derivative of G, you see, first against Z1, that will give me Sn plus 1, okay, here. And Z2, 0, Zn, 0. Finally, Sn plus 1, Z1. That's what I have for the first row. Second row, similar, I'll skip that to the nth row. In the nth row, you see, I will have 0, 0, until I have Zn. That will give me Sn plus 1. For Sn plus 1, I have Zn. Last row, I just have 1 here. 1 here. Okay. So you see, now I'm having an upper triangular matrix. In the diagonal, I have n Sn plus 1 and 1, 1. So therefore, the Jacobian here would be, as just still the product of the diagonal. So it's Sn plus 1 to the power n. So coming here, I'm just going to write this by change of variable, the density formula. This is equal to Fs1 to Sm plus 1. Okay, what I have here. And I'll apply G Z1 to Zn Sm plus 1 inside times the Jacobian absolute value of G dot at Z1 to Zn Sm plus 1. Okay. So based on what we have, right? So you see this first density, I put a G function inside. I will evaluate at Z1 times Sm plus 1 to Zn times Sm plus 1 to Sm plus 1. That's the density. And the Jacobian, we already said it's Sm plus 1 to the power n. Okay, now I'm going to evaluate this density based on what I have here. So you see, in this density, I only need, in this density, I only need the last element to be in the density function and the condition here. So you see, what's the last element? Sm plus 1. So it's actually exponential Sm plus 1 minus Sm plus 1, same as here. And now the indicator function, now here, it becomes, so this is translated to expressing it as z1, zn, and Sm plus 1. So this will translate it to 0 less than z1, less than zm, less than 1. And Sm plus 1 is positive. So it becomes this condition. And sorry, we have this Jacobian, don't forget that. Okay, so finally, we obtain the joint density for this n-dimensional vector. So what's remaining is the marginal density of Sm plus 1. Once we have that, then we can divide the joint density by the marginal density of Sm plus 1 to obtain the conditional density we need. Okay, what's the marginal density? Okay, f Sm plus 1. Evaluate this at this Sm plus 1. What is that? For this, we will use some knowledge. Because the y1 to yn plus 1, they are IID exponential 1. So fact we know is that this partial sum, each of them would follow a gamma distribution with parameters I as the number in the number of random variables in the sum, and rate parameter 1. The rate parameter is the same as the exponential rate, and the first parameter I is called the shape parameter for gamma distribution. So therefore, Sm plus 1 would follow gamma with shape parameter m plus 1, rate parameter 1. And based on the gamma density formula, we can immediately have this marginal density, okay? And it's actually equal to 1 over m factorial. So this m factorial is actually from the gamma function of m plus 1, gamma at the shape parameter. And Sm plus 1 is the value to the power n. Again, this is the shape minus 1 power times exponential function of negative Sm plus 1, okay? Finally, indicator function that Sm plus 1 must be positive because the gamma distribution has a positive support. Okay, so you see, we're almost there. With this joint density star and the marginal density double star, we are left to derive the conditional density. Okay, so in order to do that, let me try to erase this part because it's less relevant for now. So moving here, then you see, based on this and this together, these two together, I would have the conditional density of Z1 to Zn, okay, conditional on Sm plus 1. And I would evaluate it at, let's say, I just let Sm plus 1 equal to that lowercase Sm plus 1, okay? I will evaluate this density at Z1 to Zn, okay? And this can be derived as the ratio of Z1 to Zn Sn plus 1 evaluated at z1 to zn Sn plus 1 divided by f Sn plus 1 evaluated at a lowercase Sn plus 1. That's it. Okay, and then you see when we do the division, it will be equal to this line divided by this line. We have a lot of cancellation. Exponential negative Sn plus 1 will go away with this. This power Sn plus 1 to power n will go away with this, right? And also, this indicator function, when this holds, this must hold, right? So therefore, it's just 1 divided by 1 over n factorial. So therefore, we have n factorial, and also indicator function, we need it. Right, that's from the numerator. So if we compare this density with what we have for the density of the uniform order statistics, you see, they actually coincide. They're the same thing, n factorial times the condition. It's just that here we're using arguments z1 to zn, we're using u1 to un here, but they're essentially the same thing. So that's why we prove that, very interestingly, if you have n plus 1 IID exponential 1, you take the sum, conditioning on the total, you look at the partial sum divided by the total, because by the nature of partial sum, these n things are monotone increasing. Then actually their distribution, joint distribution, is the same, exactly the same as the joint distribution of the n order statistics of uniform. Okay, so does that make sense to everyone? Yeah, I think this is a very interesting result for us to know. And with this, now we have the powerful tool for deriving the order statistics asymptotics for uniform 0 to 1, which allows us to derive the sample quantiles asymptotics. Okay, and here we use, in the proof, we use the change of variable density formula for twice. So we can go from, joint distribution of y1 to yn plus 1 to s1 to sn plus 1, then to z1 to zn sn plus 1, and finally to what we need. Okay, so this is the lemma. Now let's see what we can use the lemma for. All right, so one thing that's very important for us is what CLT, the central limit theorem, told us about the partial sums for the exponential one. So we call that by the CLT. What we have is, if we have I goes to infinity, okay, then root I times SI over I, the average, minus the mean. Because here the partial sums are from the IID exponential 1. So the mean is 1. Would converge in law to normal distribution with mean 0. The variance is the variance of exponential 1. It's still 1. So this is what we have from the CLT applied to the partial sums. The reason is because because of this, and we have all the y1 to yi, IID exponential 1. That's the reason. So under this setting, we have this central limit there. So now I'm interested in the sample quantile, right? So for the sample quantile, I wonder, what if my partial sum divided by the total, or I should say, what if this I, since here my S1, S2 to Si, Sm, they follow in order. What if this Si is approximately the pth quantile? That's what I wonder. So basically what I want to say is that, what if I over n, the sample size is going to, or maybe I should say n plus 1, make it easier. I over n plus 1 is converging to p, okay? P is greater than 0, less than 1, as n goes to infinity. What if I have this relationship? So I is divergent, but it's diverging at the same rate as n. Okay, and the rate is p. So if this happens, then let's see what I can say. Think about this, and I over n plus 1 is going to a ratio, right? So then let's look at this as I over n plus 1 minus I over n plus 1. Okay, look at this. What can we say? We will utilize what we have here to create this form. So you see that we would be able to write it as I over n plus 1 in the square root times root I times Si over I minus 1. So you see, it's essentially what I have here. I'm recreating this term from what I have here. So therefore, when I let n go to infinity, so n goes to infinity, and because I over n plus 1 is going to p, then I would have this conversion to, this is a root p times the limit distribution, standard normal, right? And this root p, once it goes into the variance, it becomes squared. So this is what I have. So you see, essentially, I'm showing a very interesting thing. That is, if I look at the partial sum, I divide it by the number of IIDs, y1 to yn plus 1, exponential 1 random variables. And also, I minus this I over n plus 1. Then essentially, I'm going to have a very interesting asymptotics. The asymptotics will have the variance as the limit of I over n plus 1. So this is just the first step. And in the lemma in our notes, we generalize this, okay? We generalize this to a better result. What is that? I'll just write it down directly because I think based on what I wrote here, the derivation for this general result should be obvious. So this lemma has the following 3 conditions. y1 to yn plus 1, IID exponential 1. The same condition as our previous lemma. And we also have 2 conditions. Root n times I over n minus p convergent to 0. So this means that it's not just I over n converges to p, I over n converges to p, but I know that it must converges faster than 1 over root n, so that with this multiplication, it still goes down to 0. Okay, I have a rate constraint here. And also, j over m minus q is convergent to 0 as n goes to infinity. Right? These 2 conversions are just for real number sequences, so there's no randomness involved. So then the conclusion is as follows. That is, if I have root n plus 1 times this interesting vector, okay, Si over n plus 1, the same as I have here, minus P. Sj minus Si, or by the way, I should say I is less than j, okay? I is less than j, and also I need to have this P less than Q. With those two conditions, here I have Sj minus Si divided by n plus 1 minus Q minus P. Finally, Sn plus 1, the total, minus Sj over n plus 1 minus 1 over Q. So I'm comparing the three ratios to three proportions. Okay, and I'm going to show that this will converge in law to a three-dimensional normal distribution with 3 zero mean and the covariance matrix that has a very simple form. P 0, 0, 0 Q minus P 0, 0, 0, 1 minus Q. So why is this result so interesting? It shows that the three ratios are asymptotically uncorrelated, right? So there's no off-diagonal entries in the covariance matrix. And the diagonal entries, the asymptotic variances, are simply the same as the proportions as the mean. So in the above derivation, I almost got the first result. For this one, we actually have a convergence to normal 0p. But now we are escalating it to the joint distribution of three ratios. And actually, you know, with this is the foundation for our next result, which will be based on the lemma we previously proved to connect this to the order statistics of uniform distribution. Okay, so I will leave the proof of this to you to verify, and also it's in the notes. So this is nothing difficult, basically central limit theorem extension. But what we will have next is actually, I should take my words back. The fact that they're asymptotic equivalent is not that surprising. Actually, it should be expected because, you know, Si and Sj minus Si, they don't have shared random variables. So because of IID, they are independent, and also here and here. So that's why it's expected. So given this, then I should be able to obtain the result for order statistics, which we call a theorem, because that will give us the foundation for doing the sample quantile. So let's see how this will help us with that. So I'm basically talking about, this is a detailed explanation of the rationale I explained for the previous lemma. Why do we want to link the partial sums of IID exponential ones to the uniform order statistics? Okay, so again, under the same condition here, okay, so I call this a theorem. We have three things. First of all, we have U1 to UN IID uniform 0 to 1. And we also have those two conditions for I and J. Okay, so you know, to have this is to ensure that I will be able to say UI order statistics is the pth sample quantile. You know, that's why we need this. And also Uj will be the qth sample quantile. Okay. And that's the sample quantile for this uniform sample. So the conclusion we have here is if we have root n times the what we are familiar with, ui minus p, uj minus q. You know, p and q are the population quantile from uniform 0 to 1, right? Because it's uniform 0 to 1. So the population p quantile is p. Population q quantile is exactly q. This will converge in law to a two-dimensional normal distribution. And the covariance matrix is actually p times 1 minus p, p times 1 minus q, p times 1 minus q, and q times 1 minus q. And also this is under the condition that I is less than j, p is less than q. Okay, so this result is a direct application of this result. In order to go from there, we will just use the fact that we have that previous lemma. So the previous lemma let us know that, okay, so the previous lemma let us know that this ui, uj's distribution is the same as the si over sm plus 1, sj over sm plus 1's distribution conditional on sm plus 1. So we're going to use that to go from this result based on the partial sums of the SI, the S, the SI, SJs, and SM plus 1 to go from there. So you see, with this result, we have SI, SJ, SM plus 1. The three things we need over here. Okay, so we're going to do change of variable again. And here the change of variable is to go, so we need to use the delta method. We're going to use delta method here, so we can convert SI over n plus 1, SJ minus SI over n plus 1, and Sm plus 1 minus Sj over n plus 1. We're going to convert this three-dimensional vector to my two-dimensional vectors right here. That will give me what I want. Okay, so again, it's a change of variable thing. Okay, so to do that, we need to find the g function of what I just said. Sj n plus 1. I will find this so that this is equal to okay, so what is the g function? Then it should be quite obvious, right? How can I go from here to here? So it's basically the first element divided by the sum of the three elements. That will give me here. For this, I need a sum of those two elements divided by the sum of the three elements. That will give me here. So in other words, this g function, if I write as x, y, z, it's just x over x plus y plus z. X plus y divided by x plus y plus z. That's it. Okay. And with this g function, I would be able to do the delta method. So apply delta method to here. So in other words, I'm going to apply g to these three things, g to these three things. And I also need a g dot, the first derivative, which will actually be, the g dot x, y, z. By our definition, this will be a 2 by 3 matrix. Okay, 2 rows for the 2 values and each value against x, y, and z. So, and I will evaluate that G dot at this 3-dimensional mean, P, Q minus P, 1 minus Q. So that I can do delta method. The detail you can see in the notes, but ultimately I am able to show that with this delta method, then the asymptotics for that ratio, I'll just write it this way, Si over Sm plus 1, Sj over Sm plus 1. Okay, minus, after I apply that G to here, I will get PQ. And convergent law to normal distribution. And the covariance matrix will be G dot mu, this mu vector, times this covariance matrix times G dot mu transpose. So I get a 2x2 covariance matrix. And that turns out to be what I have there. P1 minus P, P1 minus Q, P1 minus Q, Q1 minus Q. Okay. So you see, I'm done. So this is the asymptotics for this ratio. And interestingly, this asymptotics has nothing to do with the particular value of Sm plus 1. So that's why doing the conditioning or not doesn't change it. So this is also the conditioning result given Sm plus 1 because it doesn't involve it. So therefore, by the previous lemma, this is the asymptotics for Ui, Uj, or order statistics. So we're done. So we derived the sample quantile asymptotics for the uniform statistic, for the uniform distribution. And that serves as the basis for the sample quantile asymptotics for another general distribution. So I think I'll just quickly wrap up for the general result, and we'll be done for today. So for the general result, you see, let me just quickly give you a hint. Uniform, again, is a very useful thing for studying quantiles, order statistics. The reason is that we can go from, so when we go from uniform random variables to any distribution, we keep the order. The distributions are monotone transformations. So let's say that we have an x1 to xn IID with a general CDF function. Okay, so then what's the sample quantile? Sample P quantile. And also population P quantile. Okay, so given what we have there, this is, we have seen this multiple times, the order statistics, and I said this follows the same distribution as F inverse the uniform order statistics. Okay, it's that. In the sample P quantile, we can denote it by this lowercase xp. Okay, so this is the value, if you recall, this is the value where we have this, so it's defined as just a reminder, it's the value inf x such that fx is less or equal, let me see, fx is greater or equal than p. So it's the smallest possible value so that our CDF is no less than p. And we can also say that this is defined as the F inverse P. Okay, so what we have here is that the sample quantile is the F inverse transformation of the uniform quantile, uniform sample quantile. Also, the population quantile is the F inverse transformation of the uniform's population quantile. Okay, so, our delta method would play a role again. Based on what we have there, what we need is simply root n F inverse UI F inverse UP or UJ, okay, minus F inverse P F inverse Q converges in law to what? That's what we want, because this is just what we have the sample quantile, sample pth quantile, sample qth quantile. This is the population pth quantile, population qth quantile. And finally here, right? So it's just what this distribution, what this transformation is. So here we know that we need to take the F inverse derivative and evaluate the derivative at P and Q, right? What is that? This is a calculus question. What is the derivative of an inverse function? Actually, it is known to be the inverse of the derivative of this function before the inverse. That's the inverse of a CDF, that's a PDF. Inside the PDF, we have F inverse X. Okay, so if this is something you're not familiar with anymore, just check the derivative of inverse function. That's exactly what we apply here. So then we apply this to P and to Q. Okay, so therefore we have what? PDX F inverse P. So put it here. We just have F inverse P. That's our population quantile, XP. Okay, so that's the derivative, and we'll square it, we'll square the derivative vector in the covariance matrix. So putting it simple, this covariance matrix will have this form: P times 1 minus P divided by probability density function evaluated at the population quantile and square. P1 minus Q F XP F X2. Okay, and same here. P1 minus Q F XP F XQ. Finally, Q1 minus Q F XQ square. Okay, what's the intuition behind this result? And also, just for your information, this is just XP, this is just XQ, and this is just, following the same distribution as the order statistics, sample quantile. Okay, so what's the intuition behind this? It's actually very reasonable. So think about it. Whenever the density, the probability density function has a large value, you would have a larger denominator, so a smaller asymptotic variance. So what it means is that if you are using the sample quantile, sample pth quantile to estimate the population pth quantile, then if your density is high at the population quantile, it means that you are likely to have more data points around this P to support this estimate. Then you can estimate this population quantile more accurately. So this is likely to reflect the effective sample size around this population pth quantile. That's the intuition. And you see, besides that, we will also consider P and 1 minus P, this product, because, sorry, we are not done yet, but we will be done in 1 minute. Yeah. So, and also so you can see which part of this is maximized. It's actually 1/2, right? 1/2 is giving you the largest product, P times 1 minus P. So that means that you can estimate the middle, the the 50% percentile much better than you do with the endpoints. Because basically this asymptotics will fail if P is 1 or 0, because the asymptotic variance will go down to 0. So that in that case, we need to take care of using the extreme order statistic we talk about, the minimum, maximum. And if you recall, we need to multiply by n instead of root n in that case, because they converge faster than root n. And here we're just talking about things in the middle, right? P and Q are away from 0 and 1. Okay, so I guess we have to stop here for today. So because of the technical issue, it went longer than expected. But we'll try to come back to this again next time. But basically, we have finished the sample quantile discussion. Okay, so bye everyone in the class.